guys. So today we're going to be talking about the auto-ionization of water and the pH scale. So an amphiprotic species can behave. We've already discussed that water is amphiprotic and amphoteric. Now, what it can actually do is it can undergo this process called auto-ionization or self-ionization, where you could have two water molecules that they're moving around and maybe they collided to each other, and all of a sudden, okay, both of the water molecules have enough kinetic energy such that when they collide, a proton transfer occurs. So one will literally steal a proton off another, and this is what this sort of reaction. This is sort of what this reaction that goes to equilibrium describes. That it describes that water molecules, they just sort of exist. However, maybe one will collide into each other really fastly and produce ions. And the reverse is true. That okay, now what if that proton transfers back and forth, and you get what is essentially equilibrium. Now, the equilibrium constant for this reaction is given the special designation of ion product constant, Kw, which is equal to 1.00 times 10 to the minus 14. Those units, mole squared, something. Mole squared cubic decimeter to the minus 6. Cubic decimeter to the whatever. Those units at 25 degrees centigrade. Note that pure liquids and pure solids. Note that water and solids don't show up in equilibrium expressions, so therefore we can simplify it to this, which is usually written as this in a textbook. This equation holds true for all aqueous solutions, so even if H plus is present in basic so even if there's a bunch of H plus in an acid solution and a bunch of OH minus in an acidic solution, you will always get that you will always get that Kw is equal to this, more or less. And at neutral solution and at all temperatures, the following is true. And a neutral solution will have equal amounts of H plus and OH minus. An acidic solution will have more H plus than OH minus, and a basic solution will have more OH minus than H plus. Next, we talk about the pH scale. Now, given how small Kw is, right? Given how small it is, small changes to it, like 1 times 10 to the minus 14, that's a really small number. And even if we go H plus concentration is like 1 times 10 to the minus 7 molar. That's really small. So therefore, any change that you make to it, even if it's small, will have big effects on the acidity of a solution. So it wouldn't make sense to have a scale that it would be exponential in nature, and exponential stuff. I'm sure at the time of me recording this, we are going through a bit of a plague, the coronavirus plague right now, and that's a good example of exponential growth, and we can just see how the numbers go up really quickly. So, sort of to get our minds around it, we turn it into a logarithmic chart, and this is what pH is. It's a logarithmic function of base 10 of the H plus concentration. So pH is equal to minus log of H plus. The P there is just minus log. And the reason it's minus is because so that we can get rid of these minus signs of the exponents there. But the idea is that we use a pH scale because small changes in H plus concentration will cause big changes in H plus concentration just because the amount of H plus is really small. So we take it to a logarithmic scale to sort of get a better sense of the change. And then we could also use POH, which is just that. And then POH and pH are related by Kw. Also, too, if pH is minus log H plus, then H plus is just 10 to the minus pH. Those are just sort of inverse logarithm. That's just sort of converting between logarithmic form and exponential form. And then here we can use the laws of logarithms here to get a formula for not Kw, but what would be the minus log of water Kw, which is pKw. So if we take the log of both sides, the negative log of both sides, we have this. We have this product here, which we could split into this sum because laws of logarithms. That's how it works, and this is defined as pH, this is defined as POH, and this is defined as pKw. So pH plus POH equals 14, which is pKw. Here's a little summary chart sort of explaining everything we've done. Lastly, we go through log sig figs. Basically, for logarithms, this number here doesn't. Any numbers after the decimal count for sig figs, more or less. So if you have 3 sig figs, you round it to 3 decimal places. If you have 2 sig figs, you round it to 2 decimal places. Your pH. Don't really have any special explanation for it, so there's that. Lastly, we can calculate the pH of very strong acids and strong base solutions by simply doing minus log of H plus concentration. Now keep in mind that, say for example, if we go here, you can't just do the acid concentration. So for example, let's say we had 1 molar H2SO4. You couldn't just do negative log 1, because when we do the reaction here, when we ionize it, we get 2. We get where's my mouse? Okay, there it was. So we get 2H plus and S. Oh my god. 2 minus. We get 2H plus here, right? So since this is 1 molar, and assuming the volume is the same, we can assume that molar and moles are proportional to each other. This is actually a concentration of 2 molar, the H plus here, because it splits into 2 protons, and since for every mole of acid there's 2 moles of H plus ions, it would imply that for every molar of concentration of the acid you would get twice that concentration in H plus. So you actually have to take the negative log of 2, and you can plug that into a calculator, but you can't just. My point is that you can't just go mindlessly applying formulas. You have to actually think about these things a little bit. And then the similar sort of situation with to get the pH of a strong base, you can get the POH and then use the relationships I showed you earlier, which 14 equals pH plus POH, to get rearrange for pH and solve. pH meters, you just have to know they exist. So that's it. And with that concludes the video. Thank you for watching. Don't forget to like and subscribe.